Today we're going to talk about nuclear physics. Last week what we did was sort of give an introduction to quantum mechanics and try to get everybody at the same level. And I hope that we all are right now, because we're going to use quantum mechanics now to explain some nuclear properties. But first we need a number of definitions, a number of thingies. So here's my question to you. What is a nucleus? Just making sure that everybody's on the same page before we start. Sharp, one sentence definition of a nucleus.
Center of an atom.
The center of an atom, sure.
Neutrons.
Center of an atom. Okay, I like that. And as you all know, the center of an atom consists of particles themselves, namely, well, your own role. Protons and neutrons. Okay, there we go. Now these are typically called nucleons. The combined of these two. This, by the way, is not just a matter of nomenclature. There's actual mathematics involved in treating these two particles as if they were the same particle with slightly different properties. You can do all kinds of interesting quantum mechanics and group theory on them. So there is a school of thought that says, well, it's actually the same particle with only a small difference in charge. Well, it's not a small difference. One of them has such and the other one has zero. But from another point of view, they have almost exactly the same properties, because they have the same mass up to a very small percentage difference, and they have all the other properties exactly the same. So they have the same mass. Just out of curiosity, does anyone know what the mass is? Plus, minus? Just order of magnitude? It's probably small. It's a small number. Well, these little factoids, either you know them or you don't. And if you don't, here's the number. 1.6, which for some reason is a number that pops up all the time in nuclear physics, times 10 to the power minus 27 kilograms. Both of them. Again, there's a small percentage difference. That has something to do with the binding between the quarks. I'll get back to that in a second. Well, one of them has a certain charge. This one has zero charge. So the charge of this one is 0 coulombs. Charge of this one. Elementary charge. Again, it's just you either know the number or you don't. 1.9. 1.9.
1.6. 1.6. And minus 19.
There we go. And again, it's 1.6. Well, 1.67 in this case, but sure. So abbreviated, it's probably 1.7 or so. Minus 19 coulombs. What's a spin? They have the same spin. Classically speaking, how fast it orbits its own center of axis. Again, quantum mechanically this is not the case, but it has this property that we call spin. It has all the mathematical properties as if it's something rotating, except that it isn't. What is that number? We are going to need this later on, so this is why just giving this little overview.
Is it 1?
It's not 1.
It's an integer though, right?
It's not an integer, no.
It's a half integer particle?
It's a half integer particle, yes. It's going back to last week's lecture, it's a fermion. And this is why it's so ridiculously important that we made that distinction last week, because fermions obey very different quantum mechanical rules than bosons do. Fortunately, because if you remember, one of the things that I told you last week is that electrons are fermions, and if they weren't, they were bosons, all of them would just collapse all back to the first orbit, the first bound state, which would mean that all matter would be unstable. Not unstable, they will be inert. Maybe that's the way of putting it. There would be no reason for electrons to configure themselves over all the orbits. So there would be no reason for chemistry. So the fact that fermions are bosons is a good thing. The fact that protons and neutrons are fermions, have half integer spin, is also a good thing for reasons that we will see later. So, but we do need the spin. Yes, it's half integer, but is it 1 over 2? Is 1 3 over 2, 5 over 2? Again, either you know it or you don't. It's 1/2 particle, spin 1/2. That also means that it comes in two varieties, spin up and spin down, just like electrons do. Now they have all kinds of other properties as well, which are not ridiculously important for what we're going to do today. So these are the important ones, and as you can see, they're pretty much the same particle. So this is why people have a tendency, if they really don't care that much about their electrical attraction, suppose, say, that we're just going to look at what protons and neutrons do on the influence of the strong nuclear force, which has nothing to do with charge, then they are the same particle. So this is why people tend to call this one and the same particle the nucleon. So whenever you see in your book Martin or whatever other text the word nucleon, they really just mean proton or neutron. And again, it's not just nomenclature, it actually means something. It means that under strong nuclear force, there's no difference between these two. The only difference that presents themselves is in their electrical charge, and a very, very small mass difference. This is going to be important later on. Nucleons. Right. If you're making notes of this, make sure that this whole spin 1/2, that you remind yourself that this means that they obey the Pauli exclusion principle of last week. Pauli exclusion principle. In other words, if you recall from last week, that means that no of the same particle can be put in the same state if they have exactly the same quantum numbers. Yes?
So how come the Pauli exclusion principle doesn't differentiate between protons and neutrons?
It does.
It does?
Yes.
Okay.
Because there are some other properties, except for the charge, that they do have different.
Okay.
Which is it's this thing called hadron number, but we don't have to worry, or baryon number is actually the right word, which is something to do with the configuration of the quarks. And later on, lecture I think 4 or 5, when we're going to talk about QCD, quantum chromodynamics, the underlying theory of quarks in more mathematical detail, then that difference becomes more apparent. So again, they're the same particle as far as all of these properties are concerned, except for the charge. But I'm lying a little bit because they also have this other property that's called baryon number that is going to be important, but not for today.
So that's why they're allowed to occupy the same space?
Yes. So if you have a quantum state and you're going to put a couple of quarks in, a couple of nucleons, you can put 2 protons in there, spin up and spin down, and 2 neutrons. Yeah. Because they are really different particles because of this baryon number thing. So, yeah. Okay, so yeah, the nucleus, center of an atom. So here we go. Here's the center of an atom. There's a couple of protons in there. There might be a couple of neutrons in there. And then you have the electron orbits. Of course, we're not going to worry about the electron orbits. We're just going to talk about the nucleus today. So this is everything that we're going to talk about. What is the typical size of this? Again, a number that you either know or you don't.
10 to the minus 15 meters.
Exactly. The order of magnitude is 10 to the minus 15 meters. We call this unit the Fermi, after the nuclear physicist. The strong nuclear force is that thing that binds the nucleons together to make a nucleus. And when they were first looking at these things, nuclei, Rutherford and his experimental companions at the beginning of the 20th century, they were very puzzled by this thing, because they did find out, Rutherford himself, he found out that the nucleus consists of a very small thingy that has a positive charge. Before that time, it was in principle possible that an atom did not consist of a nucleus and electrons orbiting them. But it was just this jelly-like substance that was plus with a couple of electrons in there that were minus, and combined they made 0 neutral charge. But then when Rutherford did his experiments, he found that if you shoot a couple of particles on this thing, this atom, some of them bounce back, exactly back. That would not happen if it was some goo-like substance or so. Also, you can derive a formula, which is a famous formula in both classical and quantum mechanical physics, called the Rutherford scattering formula. That tells you how many particles you would typically expect to bounce back. And he found that the formula agreed very well when he assumed that the nucleus, first of all, that there was a nucleus, this thingy in the middle that was positively charged, and that it was very small compared to the orbits. These distances, again, I'm talking very classically here, because you know that these are not actually, there's a Heisenberg uncertainty. You don't know exactly where it is. But you can sort of average these things out. This number is about 10 to the minus 10 meters. It's called an angstrom. And the order of magnitude difference between this and this is about 100,000. So that's a ridiculously small pit, this nucleus, this core. So when you see these pictures, they're usually out of scale. It's really small. Okay, so the puzzling thing for Rutherford and his experienced companions was, well, if these plus charges are combined together somewhere in this nucleus, on this very small space, how come the Coulomb repulsion doesn't just pull the thing apart again? Because electrically, they don't want to be together. At some point, they found out there were these other particles got neutrons, but that doesn't solve the problem because they don't balance out the pluses. Well, are there electrons in there? No, there are no electrons in there. So nothing is being balanced out. So the only option there is that there is this other force that binds these things together, and it's called the strong nuclear force. We made an overview of these things last week. So this is bound together by the strong nuclear force. And I want to make a distinction here that is usually implicitly made in textbooks and by lecturers. Namely, that the word strong nuclear force is usually meant for two related but different things. You have this strong interaction between particles, which is the force that binds quarks together. That is one definition of what you would call a strong nuclear force. And but there's also people that when they use the word strong nuclear force, they mean the force that pulls the protons together. Of course, they're related because the quarks pull themselves together, the protons pull themselves together, but they are different forces. There are different manifestations of the same thing. So which one is meant by which author is really just a matter of taste. How that author decided to define the strong nuclear force. And I'm going to be sloppy in my speech here. So I hope from context, from this moment on, I will almost exclusively mean this one. The protons are bound together. At some point, when I'm going to talk about this QCD in a couple of weeks, then I'm going to use strong nuclear force as the thing that holds the quarks together. But right now, strong nuclear force just means that stuff that keeps the protons together. Of course, these two things are related. Again, if the quarks are bound together, then you can imagine that there's also some sort of force that keeps the protons together. And I want to make that distinction clear by an analogy. So forget about nuclear physics just for a second. We're going to go to chemistry. Now, I'm not a chemist. There's people who can tell you a lot more about these things, but fortunately I'm a physicist enough that I can explain the analogy. Forget about the strong nuclear force. Let's talk about the Coulomb attraction. Okay? Suppose you have an atom here. And an atom, as you know, this is the whole atom, not just the nucleus, everything together. As you know, it's neutral, electrically neutral. Zero charge. But within there is a plus and there is a minus. It's a hydrogen atom, say. Plus and a minus. Same thing with a molecule. A molecule by itself is electrically neutral, but there are pluses and minuses in there. And as you know, let's make a molecule out of this, as you know, molecule. You could in principle have that the molecule is built up in such a way that there's a lot of pluses on one side and a lot of minuses on the other side. Again, the whole thing by itself is neutral. There's just as many pluses as minuses, so the whole thing is neutral. So you would think, if you didn't know any better, that this whole molecule itself will not attract anything electrically. But it does. Because this part has a tendency to pull on. We have another molecule here that happens to have a couple of minuses on that side and a couple of pluses on that side. Even though this one is neutral and that one is neutral, there is an attraction between them. The pluses from this one and the minuses from that one pull on each other. Right? So what we have here is, well, a situation that's analogous to that situation in nuclear physics, namely that even though these things themselves do not have neutral charge, there is an attraction between them. Here's the actual attraction. This is the fundamental force, this one. And this one is sort of a direct result of this other force. It's a lot weaker too. By the way, do you know what it's called?
Which one?
This one.
Van der
Van der Waals. Those are Van der Waals forces. So the Van der Waals forces are really just electrical forces that sort of leaked out their neutral environments. It's a very weak force, because ultimately these things are neutral, so it's a very weak force. This is why Van der Waals forces are Van der Waals bonds are very easy to break. This is very analogous to that situation over there. This is the fundamental one, just like this one is the fundamental one. So the quarks bound together as protons and neutrons would, if you didn't know any better, would have no attraction to each other, but they do. Just as you have this distribution of the electrical charges within an atom or a molecule that allows them to pull on each other even though they're neutral themselves, you have the same situation here. The quarks bound together as protons and neutrons might be neutral, color neutral as you would call it in this case, might be neutral by themselves, but part of it leaks out and that binds the protons together. And that's the distinction that I'm making right now. This one is the fundamental one, just like this one is the fundamental one. So a part of it leaks out. In this one, it would be called the Van der Waals force. And in this one, it's the thing that holds the protons together. Again, when I talk about the strong nuclear force, in this lecture I'm exclusively going to mean this one, the Van der Waals analogy of the electrical force. That's the one that I mean. In a couple of weeks, we're going to talk more about this one. We're going to talk about QCD. Okay, that's that. Any questions so far? Nope. Okay, well, here's sort of an overview of nuclear physics. So Rutherford and friends decided, well, there must be some force. Had no idea about this one, but they knew that this one had to exist. And they called it strong nuclear force. When you do the experiments, of course, it takes a couple of decades before you get all the information out, but when you do the experiments, you find a couple of interesting properties of this force. One of them is that it is extremely short-ranged. The force doesn't go that far. Second property, there's so much interesting quantum mechanics going on right there. I can hardly resist telling you all about it, but just stick to the program for a second. I'm going to mention at least one little tidbit of this, okay? The fact that it's short-ranged tells you something. In quantum mechanics, or better put, quantum field theory, interactions between particles, whether they are charged particles or color particles or whatever, are mediated by photons, say, by bosons. There are these particles that tell other particles what they should do. We talked about that last week. The fact that this is short-ranged means that these particles that are exchanged between two protons that tell each other how they should behave, the fact that that these particles don't go that far means that they decay at some point. And in quantum mechanics, things only decay if they have mass. So you know now already, just by the fact that it's short-ranged, that the particles that tell protons what they should do in each other's vicinity are themselves massive particles. You can even, by Heisenberg's uncertainty principle, give an estimate of how much massive these things should be. And they did that. They made the estimation. And when they found these particles, they were the pions, they found that they were exactly the right mass range. I mean, this is quantum mechanics. What we did last week allows you to calculate, to just predict what kind of particles are exchanged between protons. Okay, I decided to stop myself for a second there and just stick to the actual program. Yes?
Wouldn't be gluons the particles that
No, because the gluons are the particles that bind the quarks together. And I was talking exclusively about these. But you're exactly right. The quarks mediate the influence to each other by sending out gluons. This is the QCD lecture in a couple of weeks. Just like the particles between these are the photons. But in this case, the protons also mediate something to each other, and these are the massive particles that we call pions. And for people who are interested, if you're not interested or don't follow this particular little tidbit, forget about it because it's not important for today. The particles that are sent out, these pions, are themselves mesons, particles made out of a quark and an antiquark. If not important for the rest of the lecture for today. Okay, so two properties. They're short-ranged, the strong nuclear force, and it's strong. It's a strong force. As you can see, physicists are not extremely original in their nomenclature. They decided that the strong force, let's call it a strong force. Later on they found a weak force. Let's call that one the weak force. That's how they do it. But by strong, I mean ridiculously strong. It's much stronger than the electrical force. The repelling of the protons is a lot. It's a lot weaker than the strong force is. Again, that's a good thing. It will become important though, because if you want to do the full calculation of how these protons and neutrons attract each other and form a nucleus, the first thing you do is calculate how strong this nuclear force is. And as corrections, you can add the repulsion between the protons. In fact, this is one of the big exercises for homework that we're going to discuss on Friday. See how far we get. Okay, now when I study these things myself, in one of the books that I use, and I think it was Introduction to Elementary Particles by Griffiths, he made a nice analogy of this. He said the strong force is like the arm of a heavily muscular boxer. When you're within range, the push or the pull or whatever is very strong. If you just happen to be out of range, the force drops off immediately. If you're just 1 centimeter out of the range of this boxer's arm, you don't have to worry about being punched. Not so much with the electrical force though, because the electrical force, of course, goes down as 1 over r squared. So that will be a boxer with an infinite arm. It's just that the punch that he gives you becomes smaller and smaller by every step that you take away. Not this one. This one is actually such that if you step away enough, you don't feel it at all anymore. So if you have to make a plot out of what the force looks like, of course in quantum mechanics we never talk about Newtonian forces, but just as an idea, we talk about energies there. Force, oh, there you go. This is distance. What is this distance? That is this distance. Order of magnitude 10 to the minus 15. In fact, if you want to do actual calculations, a very good number to start with is about 2 times a Fermi. That's about the range of the boxer's arm in this case. It's such a good analogy that I wish I made it up myself, but I didn't. It's Griffiths. Then 2 to the times 10 to the power minus 15. Okay. We're going to use this later on because I'm going to actually calculate with you today how the protons and neutrons are bound together. We can use that using the quantum mechanics of last week. And what we will find, and that is the most important thing that we're going to learn today, is that there are combinations of protons and neutrons that, for reasons that will become apparent when we do the quantum mechanics, are extremely stable, much more stable than the other ones. This, of course, you know, because there's many isotopes. You have 100 odd or so different elements, and they all come with different amounts of neutrons. So in all, there's about 400 or 500 different isotopes. Most of them are unstable. They decay. A number of them are stable, and there's, well, a number that I guess are stable because they last for tens of thousands of years, or millions of years, or billions of years, but they do fall apart at some point. Now, we can make predictions out of that just by using quantum mechanics. And I'm already going to give you the answer to the problem. Because when you do the experiments, you will find that there is a sequence of numbers that if your number of protons in your nucleus or your number of neutrons obey this sequence, then that particular element, that nucleus is going to be extremely stable, much more stable than the other ones. Here's the sequence. I only know the first couple of them by heart, so I had to look up the other ones. 2, 8, 20, 28. This moment on becomes experimentally a little less certain, but especially the first number of these you can trust blindly. These numbers, if your number of protons or neutrons obeys one of these numbers, your nucleus is going to be very stable. Yes?
Are these the so-called magic numbers?
Yes, those are the magic numbers. Just a second ago I made a comment about physicists not being very original in their naming, and I always found this one extremely interesting. The magic numbers. These are called the magic numbers. And if we are to make a definition out of this, let me grab another pen. If we are to make a definition out of it, then I guess the definition would be the amount of protons or neutrons that make the nucleus relatively stable. There we go. Let's immediately start with an example. Suppose that I took a couple of protons, want to bind them together, see if I get something stable out of that. You know what? Let's make it as simple as possible. I'm going to take 2 protons, glue them together. This force overcomes that force very easily, so it sticks together. There we go, you have a helium nucleus. So that's already stable because one of the protons and neutrons, one of these 2 kinds, obeys the sequence of magic numbers, the number 2. We can make it even more stable if we're going to add a couple of neutrons to the mix as well. Let's put 2 neutrons in there too. This is called double magic because both the protons and the neutrons, yeah, that's the actual name, yes. It's double magic. Both the protons and the neutrons obey one of these sequences, one of the numbers of this sequence. So one of the most stable particles that you can get is this combination of 2 protons and 2 neutrons.
Iron?
It's not iron, no. No, iron, no. 2 protons already is helium, yes? And iron is like 52 or so. Yeah, sorry. The stable element of iron is about 52.
It's the most stable nucleus, isn't it?
Yes, exactly. Again, this is something we're going to actually calculate today. You can measure these things. You can also calculate them. And we're in the business of calculating stuff, so here we go. No, this particle, this example of 2 protons, which by definition makes it helium, and 2 neutrons, and you're all familiar with this notation, I would think, yes? Over here you have the number of protons and neutrons together. Already 2 protons plus 2 neutrons makes you 4. The fact that it's 2 sort of negates the necessity to write down helium because it's by definition helium, but there you go, this is how you note it, how you write this. This thing, this nucleus, forget about the electrons, I'm not talking about the electrons today. This particular nucleus is ridiculously stable, it's double magic. It's called an alpha particle. Just for this reason, it has its own special name that we call an alpha particle. And now already we've done some work here because when Rutherford and people who studied these radioactive substances, curie and such, they found that there were all kinds of different radiation that could come out of decaying nuclei, and just out of historical reasons they decided that the first one that they found they called alpha radiation. Had no idea what it was, they called it alpha. And the second one they called beta, and then they found out there were 2 types of beta radiation, and there was this other one that they called gamma, and ultimately they found what each and every one of them was. Rutherford himself found out that this alpha radiation is indeed 4-2 helium nuclei that's being sent out by a decaying nucleus. He had no idea why this particular combination of protons and neutrons would stick together, so you have this big thing that's called a nucleus of some very big unstable element. And it would just split apart and it would send out something. Why, of all the decay products, of all the ways that it could be split apart, why would this particular piece resist the Earth to fall apart itself? This because it's double magic property. So we've done a lot of work already. We now know what 4-2 helium is, and we now know why it is stable. Of course, the big work is in here, finding these numbers. And in fact, that's going to be a big chunk of what we're going to study this week. All right, shall we make an attempt? Okay. Here's the bad news. I'm going to use quantum mechanics as a very crude approximation. I'm going to put in something, and this crude approximation will indeed give us that number, not so much the other ones. But in a sequence of steps, some of which you're supposed to make as an homework exercise, you're going to find the other ones as well. Here's a personal anecdote. When I studied nuclear physics in university, we're talking 2002 now, I had this professor who was a theorist, and he talked about quantum mechanics, and he talked about nuclear physics, and so I studied that. I was going to be a theoretical physicist myself, so I thought it was very interesting, the approach that he took. The exam was an oral exam by an experimentalist, this guy who did all the experiments, who was in fact in charge of one of the supergroups here in the Netherlands for B physics, B quarks. So I studied that, went to the oral exam, and then this other guy asked me all kinds of experimental questions. How does this experiment work? I said, I have no idea. I literally had no idea. I never studied that. I mean, what I studied was how to do these calculations. And he asked me 4 or 5 of these questions. We're 45 minutes in, and I couldn't answer any of these questions. And I thought, well, I'm going to fail this exam stupendously. And then I told the guy, well, this is obviously going nowhere. You're asking questions in the direction that I didn't study, so might as well just, stop everything, and I'll come back at some point when I've studied the experiments as well. And then he said, well, what do you know? It's always a good question to ask somebody, but what is it that you know? And it so happened that I had taken the time a couple of days before to actually try to calculate these things myself, because the original course only gave these numbers as a sort of postulate. Well, there's quantum mechanics that tells you these numbers, and I thought, well, let's see how far we get. So I did that, blah, 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 and I found indeed the first couple of notes up until here or so. And then this other guy asked me, so what is it that you know? And I said, well, I can sort of calculate the first couple of these. And then he asked me to repeat that just there and then, and I was fortunately just happened to have it very fresh in my head, so I was able to do it. And then I passed the exam, even though I don't know anything about experimental physics up till this day. I have no idea how to measure these things. So I'm going to repeat that calculation right now with a couple of modifications and see how far we get. And this is where your contributions are going to be valuable, because last week we spent all this time to get everybody's quantum mechanics up to the same level. We're going to need an equation that's going to give us the energies of the nuclei, the nucleons. How much energy every nucleon is going to have. In other words, I need an eigenvalue equation. Something that tells me what a measurable quantity is going to be, and if you remember from last week, that's an eigenvalue equation. And it's a very specific eigenvalue equation. Not just any eigenvalue equation, it's the eigenvalue equation of which the eigenvalues are the energies.
The Schrodinger equation.
That's the Schrodinger equation. So let's start with the Schrodinger equation. Thank you. Going to keep that number here, the magic numbers. Schrodinger equation. These properties I'm going to use in a second, so I'm going to leave them here. This I don't need anymore. Now, as you know, the Schrodinger equation is exactly that. It's an equation that tells you, if you tell me under what conditions a particle is moving about, what its energy is going to be, and what its state function is going to be, what its eigenfunction is going to be. Here's a Schrodinger equation for a single particle. There you go. That's what we're going to solve now. Now this is the mass of the particle that we're going to look at. I just written it down, 1.6 times 10 to the power minus 27 kilograms, regardless whether it's neutrons or protons. But let's forget about that for a second, we're just going to call it mass. This thing tells you what the kinetic energy is going to be of this one particle, this nucleon floating about in the nucleus. This is potential energy, I'm forgetting this thing here, right? And this tells you how this state function is going to move about in time. What are we going to use for this one? The properties that we're going to need are somewhere on the board. So if we erase everything so there's not many options left. Because you know, sorry?
Wasn't Q over 4 pi epsilon?
If we're going to talk the electric propulsion between them, yes, you're right. But we're now going to talk about the strong nuclear force. So the thing that tries to keep protons and neutrons, or protons and neutrons together. So forget about the electric propulsion. You're right though, there is electric propulsion. And one of the exercises later is going to be put that in some way. But for now, as a first order approximation, just use the nuclear force, the thing that tries to bind them together. And it has two properties, short range and it's strong. The strong part we are already implicitly using by neglecting the electric propulsion between them. Now we have to put in the short range version. Yes?
We could just use the potential we use for square valves, because the force drops off
okay.
very quickly, kind of like a valve.
Alright, let's use that. That is, of course, a very good first approximation. What we're going to do is, if we're going to make a graph of the potential energy as a function of its position. By this I mean, by R, I mean the distance between two nuclei. I'm sorry, not the nuclei, nucleons. Doesn't matter if it's a proton or neutron or proton and a proton or neutron or neutron, because for the strong nuclear force, these are pretty much the same anyway. That was the point that I made before. So whatever is going to come out of this is going to work for both protons and neutrons. This is their distance. How about this? And that's what you meant, right?
Mm-hmm.
There you go. That it drops off. Actually, this is somewhat wrong. Because what I have right now is that if I try to put a proton in here, it's actually more difficult because it costs me more energy to get it over there. Where it's going to be easy to put it over here. Now that's exactly not what the strong nuclear force does. It tries to pull everything together. So the picture is almost right, but not exactly. How about this? There you go. Now much more easy to put the proton in here, within this range, somewhere in this range, than it is to put it outside. This is about the distance, R0 I'm going to call it, where the box's arm doesn't hit you anymore. It stops trying to pull you in. And yes, it's a very crude approximation. We're just going to make it a square well. In real life, it's much more this arc thingy. It drops off fast, it drops off quickly, but not as quickly as I'm writing it right now, but it's a very good first approximation. There's a value here. I'm going to call it V0, has to come from an experiment. And I'm going to make this strong nuclear force so ridiculously strong that it is actually impossible to get it out. In other words, that this potential barrier is infinitely high, which is another way of saying that it's going to cost you an infinite amount of energy to get the nucleons apart. Again, it's all an approximation that we could do a lot better. We're going to work on that later, but it's much more about the mathematics now than it is about the physical details. How about this? We're going to solve this equation and only restrict ourselves to this domain. From R0 to R equals, well, let's put this number in right here. There you go. Now this is a very easy problem. Actually it's not, it's going to take some mathematics, but from a quantum mechanical point of view it's as simple as they come. Now we're going to solve it. That means that if we stick to that range, so R is smaller than R0, this one becomes a constant. So our Schrodinger equation gets this very, very simple form. V0, which is now a constant, equals this thing right there. There you go. How are you so far? Still following? In your quantum mechanics course, ever solved a problem like this? Because it looks very familiar to a very famous problem in quantum mechanics. It's not quite the same though, because there's differences that I'm going to tell you in a second. But have you ever seen a potential like this and then solved it? You know what the answer is? Maybe even by heart?
What was the sign?
There are sines and cosines in there, that's right. They're right. In fact, there are sines, because the cosines cannot be...
Pi n over a or something.
Yes, okay. Well, that's good. I was planning on going through that example, and I don't think that I'm going to. If people are familiar with it, our problem is going to be similar. It's going to be a little bit more mathematically complicated, but the general outline is exactly the same. Yes, for people who want to study up on this, it looks, but it's not quite the same as the so-called infinite potential well problem in quantum mechanics. Again, this is not this example, it's similar. And if you solve that particular problem, so you have a potential well, in other words, an infinitely high potential, there you go, and you solve this problem, just by doing the mathematics you find that the wave functions in here are indeed sines, like these. Not cosines though. Do you recall why? Because from a mathematical point of view, cosines are the solution to that differential equation. It's a second order differential equation, two derivatives. So in other words, it's going to be two linearly independent solutions, and they happen to be sines and cosines, but the cosines physically, for physical reasons, we throw away. Mathematically they are allowed, physically we throw them away. And I want to hear that argument because we're going to use a similar argument in our calculation in a second. So do you remember what it was?
Because it has to be 0 at the point of
Yes,
the barrier.
exactly, exactly. Over here, at the boundary of the wells, the function has to go to 0. But Hugo, why is that true? You're right. I mean, this is the condition, but why is that true?
Potential energy becomes infinite, so then it basically means that all of it.
Yeah. No, please go ahead.
That it cannot be there. Like the location cannot be
Exactly.
anything.
Exactly. Because as you know, this solution modulo squared tells you the probability of finding a particle at a certain position. Now, if it has an infinite steepness here, in other words, that it would require an infinite amount of energy to get the particle at this position, it's another way of saying the particle will never ever be there. Which is another way of saying that at this position, this thing should be 0. And cosines are by definition not 0 on the boundary. So you need to have signs. To put the same argument into somewhat more sophisticated form, what I'm saying here is the state function has to be normalized properly. So there we go. So we throw away the signs, the cosines. We find these solutions. How do we get the energies out? We now have the functions. They are signs. How do we get the energies out?
Just solve the Schrodinger equation.
Yes, but under conditions, yes? The Schrodinger equation gives you a certain amount of freedom in your solutions because of the integration constants that Ronald is so fond of. I heard, I have no idea. We need to have another condition that gives you the energies. In fact, let me write down what the solutions are. If you do the mathematics, again, this is all leaning on your memory of how to solve this problem in your quantum mechanics course. So constant integration, A times the sine. There you go. This is a solution if you do the math. Again, how do I get the energies out? This number energy could, at this point, from a mathematical point of view, is allowed to have any value, but not from a physical point of view. What is the physics?
Discretized?
What's that?
Discretized?
It will become discretized, yes. But how do we know? Again, I've solved now the problem, and I just have the mathematical solution. I had two solutions, sines and cosines. The cosine I threw away for the simple reason that it had to be 0 at this point and 0 at that point. There's another condition that these waves need to obey. And in order to use that condition, well, we get the energies out. And yes, you're right. Then it turns out that they're discretized. But what is the criterion?
It needs to be normalized.
The normalization is in here.
Oh, okay.
You're right. I mean, it has to be normalized. That if you take the modulo square, you integrate this thing over all the positions that the particle could be, the answer should be 1. But the best thing that can give you is this number. And I'm talking about that number.
The signs only give you integers for specific positions.
I think that is a step in the right direction. Yes. What I've put in, when I said, well, it has to be signs, here's R equals 0, and here's the other side of the potential well. This is 0. The fact that we threw away the cosines, that we did because they had to start at 0. At R is 0, the answer would be 0. Cosines wouldn't do that because cosine at position 0 would give you 1, which doesn't agree with this part of the well. There's the other part of the well. It also has to go to 0 at the other side. Now, how do you get a sine? So this thing has to be 0. Not just at R equals 0, that we already did by choosing the sine instead of the cosine. But it also has to be 0 at this side. So it has to be 0 at R equals R0. So the question that we have now here, just from a mathematical question, how can we get the argument of the sine to be 0 because the sine of 0 would be 0? Or pi, or 2 pi, or 15 pi, an integer times pi. this condition, this is physics. Translated now into mathematics, this condition tells you that 2me h bar squared at r0 should be an integer of pi. That's the only way that you can get these signs to go to 0 at the other side. So this has to be some number, we call it n, times pi. You do a little bit of mathematical algebra, you get the E out, and yes, then it's discretized. And you get the sequence of energies. I'll get to you in a second. Then you get the sequence of energies. And as you can already tell, you take the square to get rid of the square root here. It goes with n squared. Every next level has a squared amount of energy less than the other one. Excuse me, more than the other one. So there's that. Now the reason that I go over this, even though I don't do the mathematics in full detail, is because I'm going to use a similar argument in a second when I solve our problem over there. Yes, your question.
What's the symbol on the first equation, all the way to the right? After the square root.
This one here?
Yeah.
Yeah, that's my version of an R.
It's an R.
Yeah, I'm sorry, that's an R. University, I found that my 2, my R, and my Z were too similar. I solved the last problem by all my Z's now have a Z with a little bar, even in my normal handwriting now. This problem I still haven't solved, so but it's an R, it's not a 2. Okay, so this is the infinite potential well. If you don't know the details, please look it up. It's very basic quantum mechanics. The main line of reasoning is right over here. You solve the equation, Schrodinger equation, you get the sines and cosines out. Cosines is throw away because it has to be 0 at the one boundary. The integration constant is fixed by normalization, and energies are fixed by demanding to be 0 at the other side of the well as well. How is this a different problem than that? Because, well, the potentials look similar, right? I mean, you have something that goes in, and there's this deepness that comes out. It's sort of like this, but it is different though. Makes the mathematics a little bit more difficult too. So, can you tell what the difference is? Do you see the similarities? Let me start there. In both cases, it's an infinite square well with infinitely high steepness. But for some reason, I'm not going to just copy-paste this solution because there is a difference, mathematically and physically. And I want to know what it is.
Between this and the counter problem with infinite potential well.
Yes. This one here in black is not quite the same as that one. They're similar, but they're not the same.
The graph should be drawn differently. It's not infinite on both sides. Or is it infinite on both sides?
It is infinite on both sides. In our approximation, in real life it isn't.
Yeah.
Because the arm of the boxer does extend up to some point, yes.
Yeah.
But in our approximation, that is not the difference. That is very similar.
We have a ground level that's not 0. Ground potential is not 0.
That is not an issue though. I mean, you're right. I could have done the same thing here, and the only thing that would have changed is instead of E, it would have said E time minus V0. In fact, the number doesn't matter that much, to be honest, because as you know from any field of physics, the only thing that has physical interpretation, measurable defining qualities, that is a difference of energies. So your 0 point doesn't matter. I could have put it at 0 or at V0, doesn't matter. Especially if one of the other numbers is infinite anyway. So no, that's not the issue.
Sorry, we're trying to introduce a proton between R. So the third one is being...
No, you have one of them, and you try to add another one.
Okay.
Yes.
R is not an integer of pi.
Sorry?
Is the R not an R0 is not an integer of pi.
No, but that also wasn't the case here. R could be any value.
Mm-hmm.
Okay, maybe I'll drop a hint. The number of dimensions. Well, that's actually the answer, but can you tell now in retrospect how that differs everything? How that changes? I'm going to drop another hint. This is one-dimensional. There's only one way that particles can go, namely this direction. Now if I'm a proton over here, or any nucleon, and I want to add another nucleon, I can do it from all sides. This strong nuclear force, you could say there's a third property, it doesn't differentiate between angular directions. that changes something. But we're not quite there yet. Yes?
But the wave function will still be linear, will still be separable into x, y, and z components,
Yes.
right? So,
Yes.
so then would you just multiply it together?
Ultimately,
with
yes.
the
Yes.
wave functions?
When I solve the thing, I'm going to use separation of variables. That's right.
So it's the same distinction as you have between a finite well and a 3D box from normal quantum mechanics.
No, because a 3B box is rectangular. It's a cube.
Mm-hmm.
Whereas in this case, it's a sphere. That is the main difference. I wasn't planning on using those terms, but thank you for this, because it is a nice introduction. You see, if I have this nucleon here, and I'm going to add this other nucleon, that's what we're talking about now. It doesn't matter if you try to bring it in from this side, or from that side, or from that side, that gives you a circle. In all directions, it will be the same wave function. You can also come from this side or from that side, and that gives you a sphere. This r that we have here, that one, is the distance from this first nucleon in any direction. Doesn't matter which one. In this case, that case, infinite square well, that will be the only dimension, the only direction that things can go in, namely the x direction, the y direction, the z direction. That changes a lot. The fact that this is three-dimensional and that the angle in the 3 dimensions is completely irrespective of the whole problem. Nuclear force doesn't distinguish between angles, the actual directions, changes something. Now we come to another part that, again, I'm going to lean a little bit on your previous experience with quantum mechanics. There is a problem that has the same property, and I'm sure everybody has seen this and has solved this up to some mathematical detail. It's called a hydrogen atom. The hydrogen atom has the same thing. We're not talking about nuclear force now, but about electromagnetic forces. But the electromagnetic force in a hydrogen atom also doesn't distinguish between directions. This is really just me asking what my starting point can be today. Do you know how to solve the Schrodinger equation at the moment that your potential, this one, doesn't depend on direction, only depends on distance? It's called the central potential. If you don't, that's fine. Then I'm going to spend a couple of minutes talking about that, but we do need to know this. In the hydrogen atom, you have solved this, if you have solved the hydrogen atom, because that is the same problem. Okay, I think I'm going to spend a couple of minutes talking about that. So let's take a piece of board here and talk about something that is called the central potential in quantum mechanics. And central potential is exactly that. It's a situation in quantum mechanics where the potential energy only depends on direction. On distance, not direction. So it's a situation where the potential energy, which typically is a function of the vector r, so depending on x, y, and z, only depends on the number, the size of the distance. Note the difference. There's a vector here and there's a scalar over there. It's only the distance. Angle doesn't matter. It turns out that even without saying explicitly what this is, this potential energy, just the fact that it only depends on the magnitude of your vector r, doesn't depend on the directions, allows you to write your total wave function, and here's your separation of variables, as a function of r times another function that only depends on the angles. I should be more careful. These are not the same functions, of course, even though I use the same symbol. This is the r function, this is going to be the angular part. How's that? There you go. Mm-hmm. If you plugged this into the Schrodinger equation. Yeah, please, go ahead. You have a cold?
No, I'm sneezing for some reason.
Okay. If you plug this into the Schrodinger equation, and you do the separation of variables, you get two different equations. One of them only depends on the angles, and one of them only depends on on r. The angular part, so the differential equation of which this is the solution, the angular part, is the same for each and every single one of these central problems. Why? Well, for the very simple reason that every central potential doesn't depend on theta and phi. So in other words, if you separate this out, this will be the same for all problems. So the solution will be the same for all problems. Now, without giving you any proof, because the mathematics is cumbersome, it's not very insightful, I will give you the answer. This part is always the following function. It's called big Y. Depends on two indices that I'm going to introduce in a second. And this function, there are many, many tables on the internet and in the books on what these functions are. They're called spherical harmonics. You have seen these before, yes? The spherical harmonics are extremely interesting for many reasons. One of them you can already see here, because every central potential problem in quantum mechanics will have this as part of its solution, regardless of what the potential is. Also, you can very easily prove that the spherical harmonics, that you can write any function of theta and phi as a sum of spherical harmonics. Just like you can write any function, well, under certain conditions, as the sum of sines and cosines, Fourier analysis. You can do the same thing with spherical harmonics. They also form a complete set in a mathematical sense of the word. But here's the most interesting thing for our physical properties. This L value, if you do the mathematics, you will find it can only have integer values. Why? Because mathematics. There's no physics, this is what mathematics tells you. This M number can also only have integer values, but very restricted. It should be integer, and it should be somewhere in between these two values, L and minus L. Why? Well, because mathematics. There's no physics. This is just taking this one, putting it in there, solving the equation, and the mathematics tells you only allowed if L is an integer value and M is also an integer value between these boundaries. Here's an example. Suppose that you take the spherical harmonic L is 0. What are the possible M values?
0.
That's just 0. So there's only one solution.
Sure.
That's fine. You okay?
Yeah.
Here's another example. Suppose that I have L equals 1. What are the possible M values? Well, all values between 1 and minus 1, all integer values. So there's 3 of them. L is 17.
35 M values.
35 M values, that's right. Let's not list them all. It's minus 17, minus 16, minus 14, etc., all the way to plus 17. Minus 17, dot, 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 17. The number of these were 3, it's 35. Because you have from 1 to 17, from minus 1 to minus 17, and there's 0. So this, you have 35 of these. The general formula that you get out of this is that the number of M values is 2 times L plus 1. 2 times L is from L is 1 till big L. 2 times, because you also have to do it in negative, and the plus 1 is the 0 value. This is going to be physically very important, because this gives us quantization in a moment. The fact that you have solutions that only allow certain values is exactly what we call quantum mechanics. Things come in lumps, in small amounts. We already saw it here, in a much more simple example. Over here, you saw that the only values that these could have, the energies, were lumps. Discrete spectrum, as you call it. Not all values are allowed. And you can already see just from mathematics that the angular part of our bigger solution in a moment is already quantized just because of the spherical harmonics. This is why I take a moment to talk about these. Alright, so we know now how to write the angular part. Now it's this part. Again, this is just you do the mathematics. You take this one, you plug it in here, you squeeze out 2 different differential equations. One of them gave you these. We're going to forget about these ones because we will have the full solution for all of them. But the R, this part, obeys a differential equation by itself. This is one I always forget exactly what the thing is. Yes, there you go. Because this is really crappy form. Yes, there we go. becomes a differential equation in R. First derivative. That's that one. I hope you can forgive me now that I always forget what the exact form is. Plus h bar L plus 1 over 2mr squared. Yes. Plus this potential. There you go. This is the other differential equation that will come out. And now you see that this one is just much more difficult than our example that you saw just here. It's just that the differential equation happens to become more difficult because of the 3 dimensions. Now, to get from here to here is actually one of the homework exercises. You don't have to solve it though. Just show that writing your full function as a product of these two, that one of them give you these solutions and the other one gives you this differential equation. Don't solve the differential equation. That's what we're going to do here today in class. Just to show that this differential equation comes out in the first place. So for now we're going to take it as a given. And that's the situation that we have right here. Every time in quantum mechanics that you have a central potential, well, you can rejoice in happiness because at least you know how to do the angular part. That's already given for you. That's the spherical harmonics. And then you sit down in despair because now you have to solve this differential equation, which is much more difficult than the one you started out with. But then again, that's life. For some reason, nature has decided that it's just out of our reach, just slightly out of the grab of our imagination. It becomes a little bit more difficult. Fortunately, we're going to see the solution today for our particular problem. How are we on time? And we already took an hour. How's the energy? Your energy. Continue just a little bit more. At least write down what the differential equations are. Alright. Well, let's erase that part. We're not going to need it anymore. Okay. Can you see why I'm confused all the time? They look too similar. This is our problem. Implicitly, what we've done now is said that our nucleus is spherical because we've made it into a central potential. In real life, nuclei are not spherical. In fact, to talk about shapes in quantum mechanics is a strange thing in itself because then you sort of assume that you know exactly where the boundaries are, and Heisenberg tells you that you can't. But you know, as a sort of a picture, we have sort of assumed that it's a spherical thing. You can make adjustments to the theory by adding non-sphericality to it. Then your model becomes much more complicated, but also much more accurate. But again, it's only a crude approximation. Let's write down our solution. Here's one. The solution to this, r theta phi t, will be psi r, that we yet have to solve, times the angular part, that is the same for all spherical problems, the spherical harmonics. Again, that means that already from the get-go we have quantum mechanics, because L and M can only have certain values. How about the time part? Do you recall from your quantum mechanics course what that part is? It's also always the same for every problem. Because the thing also depends on t. There's no t in there yet, but the t dependence of every wave function is always the same thing. Do you know what it is?
E to the power of e to t or something.
There you go. That's the one. Again, this is also separation of variables. That if you would add here a function of t, you put it in, you can squeeze out another differential equation just for the t dependence, and it's always for every potential, regardless of whether it's central or not, is always going to be the same thing. It's that thing over there. So there we go. So this one we know, that one we know, this one we don't know. We do know the differential equation that we have to solve. That's this differential equation. life sucks. What is this in our case? The V.
V0.
That's V0. It's a constant. That's good. We have removed one R dependence. So we know that our differential equation is going to be that one. R squared, memory serves, yes. DDR, another R squared, another DDR, and psi R plus that part, H bar L plus 1. Again, if you don't know where that comes from, that's one of the homework exercises to figure that out. And plus V0. And this one is just a constant, the total energy times ER. Because you know from Schrodinger's equation that this thing is the operator for the energy, so it's just equal to E times the energy. Eigenvalue equation. Okay, we haven't made much progress yet, except for one thing, that we've removed one of the R dependencies and turned it into a constant in our particular case. Okay, now how to solve that one. This will go in a number of steps. It's really just mathematics. It's hardly going to be any physics in the next couple of steps. But I do think it's worthwhile to go through it, just to see how that works. But maybe this is about the time that we should have a break for a couple of minutes. Is that okay? Okay, I'd like to continue.
All the art like projects like
for no other reason than I was running out of ink, I'm going to continue with black now. But also makes a nice distinction on the board. This is before the break and this after the break. So black is after break, okay? We were at this stage here. We had to solve this. Again, from this point on, it's mostly going to be mathematics. And the way to solve this is by using a number of clever substitutions. Just rewrite the things that you're looking for in some other way, and hopefully this other way that you're going to write these things into happens to give you a simpler differential equation. And one of the steps that we're going to do, again, this is all mathematics, no physics involved. We're going to say, well, you know what? This thing, this R-dependent part, we're going to write as this. Excuse me. 1 over R. There you go. Now, why would you do that? Well, first of all, let's convince ourselves that it's allowed. Right? So this unknown function psi, and we're going to write it as this other unknown function u, but we're going to pull out one of the r's, 1 over r's. Why? Well, it so happens that if you then try to rewrite everything here, the differential equation becomes simpler. If people have no particular interest in seeing how the mathematics work, I'm just going to give you the outline of this. Because what we have here now is, suppose that you have now to write a derivative of psi r. It is now turned into a derivative of u over r. Yes, no? I think that's correct. And unless my mathematics is mistaken, it should give you 1 over r squared. I think that should give you something like this. Now, why is this helpful? Because by using this clever little substitution here, this r squared is going to cancel out this r squared over there. And things become more simple. In fact, a nice homework exercise would have been choose an appropriate redefinition of your psi such that your differential equation becomes simpler. And one hint you could have taken, well, let's make a substitution such that this r squared vanishes. Anyway, it's already been done for you. If you just follow the procedure, you will get this somewhat more friendly looking differential equation, which is this one. Squared. There you go. Now look at this and look me in the eye and tell me that it's not been cleaned up a little bit now. You had this difficult thingy here with all kinds of stupid derivatives, and now it's become much more friendly looking. It even looks familiar if you look at it. Because minus h bar squared over 2m times the second derivative is exactly what you had in the original Schrodinger equation. So we sort of have our original Schrodinger equation back. That's good. That means that all the techniques that we use for usual Schrodinger equations can now be applied again. Yes?
That's an h bar, right? Or
Yes, that is an h bar. Yes?
In the quotient rule, wouldn't the signs be reversed when you take the derivative? Wouldn't it be u minus r du over dr?
What sign do you mean?
In the derivative for psi sub r in the numerator.
Over here? Oh, you see. Oh, okay. You mean that there should be something here, something with a minus sign or so.
Just a minus sign.
Yeah. I think you're right. Might have missed a minus sign somewhere. The thingy below is correct though.
Yeah.
So we can just go through the calculation in a second and see if we would drop the minus sign somewhere. This one is very correct.
Okay.
Also, we have to take a second derivative here as well, so it might as well that gives another minus sign or something like that. I mean, I can assure you that this is correct. I did it on the train again a couple of days ago, 2.5 hours. Lots of time to do this. Went to Amsterdam and back 6 times last week, so lots of time to go through all the calculations. It's because of my research in Amsterdam with Nick. So these people said, we have to be physically present here, and I said, okay, 2 days a week. That's a big commute, but anyway, still sorting out how to do that. I think your minus sign goes away with the second derivative in R. I've done the calculation.
It doesn't matter, it's just a minus sign.
Okay. Well, minus signs can be important though, especially on bank accounts and such. But okay, so this is where you get. Yeah, if I look at my bank account and somebody has reversed the minus sign, I'm going to be worried. Although I've also had times where, reverse minus sign would be a good thing.
Mostly it doesn't matter.
No, that's true. So what people usually call this is a name, they call it the effective potential. Why? Because if you just redefine this new thing, your V, your original potential, plus this extra part that came from the spherical harmonics, it really is just a Schrodinger equation again.
sorry, I have another question.
Yes.
Why does it become a VR instead of the V0?
It is V0. This is the general case. But you're right, in our particular case, it is V0. There we go. Now I have to solve this. Yes.
Can I ask a quick question? Sorry.
Okay.
When you were deriving that form there to the right, this form, yes. Did you actually add in the centrifugal potential, or did you just solve the Laplacian and got that as a result of that?
It's because of Laplacian.
Okay, so you didn't actually add.
No. I didn't add it in because of my my happy personality. It's really just because mathematics wants you to.
Oh.
No, you're right. I mean, and again, going from here to here is one of the homework exercises. You can see for yourself that this one automatically comes out.
Shouldn't there be a over R on the right side under the E and the U, or where did that go?
It didn't go anywhere. I multiplied it away.
Oh, okay.
Again, we now are at the stage that we have to solve this. Now, what I typically do when I do calculations, especially if I have to lecture on something, is I close all the books and see how far I can get just by myself. And one of the things that I saw here is that it sort of looks like a Bessel equation. And if you don't know what a Bessel equation is, it's a very famous differential equation in mathematical physics. Looks like this. Bessel equation. I'm already telling you that the solution is going to be these things called Bessel equations. It's important. A Bessel equation is this. Suppose that you have a function, y is a function of x, and your differential equation looks like this. X squared times the second derivative of y plus x first derivative of y plus x squared minus some number squared, alpha, times x. This equals 0. This differential equation occurs a lot in mathematical physics. It's called the Bessel Differential Equation. The solutions are known. Out of pure originality, they're called the Bessel functions. How many solutions are there, by the way? Types of solutions.
Particular and general.
Apart from, well, there's no particular because there's no source term equals zero.
Just in general.
Yes.
Yeah.
But then there's still two different types because it's a second order differential equation. It's a linear. It only applies to linear differential equations. It's a second order linear differential equation. There's two solutions. One of them is called the Bessel function. We call it J. It has an index alpha. And this alpha is that number that happens to be in your differential equation. It's a function of x. And there's another one. It's called the Bessel equation of the second kind, which is the second solution to the Bessel differential equation. Another name for that thing is the Neumann equation, the Neumann function. For stupid reasons, in our particular context, it is the same symbol as a spherical harmonic. So please note by the index whether I mean a Neumann function or a spherical harmonic. If it has two, an L and M, I mean a spherical harmonic. If it has only one, the alpha here, I mean the Neumann function. Fortunately, in a moment we will see that the Neumann functions are going to be out of our equation because of the same reason as the potential well that we saw before, because of normalization and such. So our general solution to the Bessel differential equation is y some number a times the Bessel function plus some number b times the Neumann function. And you don't have to look for any more solutions because you know by this mathematical theorem, second order differential equation, this is the full solution. And yes, you're right. Typically, you would have a particular solution as well if it did not equal zero.
Yeah.
But in this case, it does. So,
Sir,
yes.
can I ask you if you can write down the names?
Yes, sure.
Understood, but
Absolutely.
very good, thank you.
Just for Bessel, this is Neumann. There you go. In case you feel like looking it up, these are very well-known functions. You have no difficulty finding them. Okay, now why do I write this down? Because I looked at this and I thought, well, that's sort of the same thing, isn't it? Well, because suppose that I multiply everything now by r squared. What I get here, so I multiply everything by r squared, absolutely no difficulty there, no mathematical reason not to. I get this. Here's the r squared over there. Multiply everything by r squared, then I get h bar l plus 1 2mr squared minus you agree? Multiplied everything by r squared, took the energy part in. No physics, just mathematics, just doing some rearranging. And I made a mistake. Because that one should have been out, right? That is correct. We're still on page. Help me out here. Things should be like this. I'm doing it in real time now, so feel free to check me for a second. Multiply everything by r squared. So that means that this one gets an r squared, yes. This one gets an r squared, that one gets an r squared, that's that r squared, this r squared is cancelled, that's it. Yeah, okay, it's correct. That's the one. Yes.
I'm not sure, but the in the V0 should be the other way around, or is it like that?
Which one? This one?
To the right. It's minus. No, I
Here's
didn't
a minus.
here. It is a plus.
Alright. Well, let's get rid of the minus as well then. Here's a minus. Turn this into a plus. That's a minus. It looks very Bessel-y now. Because what we have here is a second derivative times r squared, just like we have here a second derivative times x squared. And over here we have this a constant with a minus sign. And this part that depends on r squared, or where it would have been an x squared over there. It's almost like a Bessel equation. Now, I see no reason to try to solve this all by myself again if I know that the problem has already been solved by Bessel and by Neumann. The only thing I have to do is massage it mathematically in such a way that it actually is a Bessel equation. We're close. We're not there yet, but it's there. This part is already correct, right? Yeah. That would be that part. this part is already correct. That will be that part. We have a constant here. That's that part. The only thing missing is a first derivative. That's all. So if I can sort of rewrite this in such a way that I also get a first derivative in, I have a Bessel equation. I can write down everything. I have the solution, the full solution. It took me a while to find the right way. Would be a nice homework exercise. What would you do to turn this into a Bessel equation? I'm going to give you the answer, because again, no physics, just mathematics. I thought, well, you know what? First of all, I'm going to replace my r variable. There's an r over here, there's an r over there. I'm going to replace it by this other thing. Yes?
Sorry, in the final term you have the term multiplied by u, but in the Bessel differential equation it's x, and here we have r is equal to x basically.
Yes.
So isn't there a discrepancy there?
I don't see it. What I see here is r squared.
No, next to it with the u.
With the u.
Yeah, it doesn't.
Oh, geez. Oh, I'm so sorry. This should be an. Oh, excuse me. Oh, does that make sense again?
Yeah.
Okay, I'm so sorry. This should have been a y. This is a solution, not another x. Now, please make sure if you're writing this down, make sure that you correct that for yourself, because otherwise you end up with a very different differential equation.
So where's you correct?
Originally, I wrote down an x. There was a typo here. It was a y. In other words, a solution. That one, the u. That was your question. So thank you. Your question got me back to the right track again. Here's a crappy thing. When I did this on the train, I made exactly the same mistake. I don't know why, but for some reason my system replaced this one 2 times. There was probably some deeper meaning to it. Yeah, what I'm going to do is I'm going to replace this r here by... I had to pick a different name, so I decided r with the bar. It's not a vector, it just means some other variable. I decided to replace my r by this r bar thing, and the r bar is defined as this. I hope you can see why I do this. Square root. I hope you can see why I do this. It's mathematically allowed, but there's a reason. If you look at your Bessel over here, it should be x squared with a 1 in front. What I have here is r squared with a non-1 in front. Some number. So I decided, you know what, I'm going to replace my r by this thing over here. Then by squaring it, I get 2m. This thing here, that cancels e minus v0 here. And if you do the algebra, you'll also find that also cancels that one over there. So I do that for a reason. I'm very sorry, magic numbers, but I'm going to use this space here. Alright. The differential equation becomes a little bit more simple now. Right now it has become that one over here. All my r's are now going to be r bars. I have to check my notes in a moment to be really sure that I'm not making any mistakes now. So again, feel free to correct me. There you go, I think this is correct. Yes. Yes. I've cleaned up everything immensely by just replacing this r by the r bar. If you go through the algebra, you'll find that this becomes that. Much more simple, looks much more like a Bessel. Except for that one missing derivative still. Because we still don't have this part. Otherwise, I'm already there. Look, this thing is what it's going to be alpha in our case. So we're close. Here's another step, another substitution that you can make to make things easier. to look at my notes to be sure that I don't make any mistakes. All right, here's my u. I'm going to replace it by another u bar. Again, no physics, just mathematics. Can you see why I do this? The object is to get a term like this out, a first derivative. And you know the product rule of differentiation.
Yeah.
Now I have a second derivative here of this u, but my u I've now replaced by a product. And then the second derivative will give you a number of terms. One of them is going to be a first derivative. That's no coincidence. I do this on purpose. I replace this in such a way, this thing by a product, in such a way that my product rule of differentiation will give me a first derivative as well. Now here's the final one. You can easily check all these steps by yourself, by the way. So I'm just going to write down the final differential equation. Again, just mathematics, no physics. So expressed in this new variable r bar, I will get here's my first derivative that I, by construction, made sure that it's going to be in there. Plus r squared minus L there you go. You will find that there's another 1 over 4 that appears now all of a sudden. That's because of the derivatives. This product rule will also give you some additional terms except for the one that I wanted. And it turns out that that one is going to be 1 over 4. If you do the algebra, the differentiation, you will find that this is the case. Now, this is my final, here's a square, here's my final differential equation. Again, all mathematics. I just started out with the Schrodinger equation, just did some rewriting. In such a way that this thing is now exactly a Bessel equation. Second derivative times thing squared, first derivative times thing squared minus a number. That's exactly the Bessel differential equation. I know the solutions then. U is going to be some number, j, Bessel function. What is my alpha? I mean, I made this into a Bessel.
What's the L times, yeah, that term?
There it is alpha.
Alpha squared.
Alpha squared, you're right. Yes, you're right. Thank you. So I hope you forgive me that I'm not going to write down square root of this big number here all the time. Just going to call it alpha, okay? Mm-hmm. There you go, alpha. As a function of r bar plus b times the Neumann alpha r bar. There you go. And we've solved everything now. We have solved the Schrodinger equation. We already knew the angular part, spherical harmonics. The time-dependent part is always the same thing, e to the power minus e I e t over h bar. The only thing that was difficult was the r-dependent part, but by massaging everything mathematically, we got the Bessel equation out, and there's a solution. There we go. Life is beautiful, it really is. Okay, so far the mathematics. Now we can get back to physics. You're happy, Bill, right? I mean, we're going to go back to physics. Here's the physics. We have two constants of integration now, a and b. Mathematically, they should be there. You can assign any value to them. What boundary conditions do we have? What conditions does this wave function have to obey? There's a number of them. I'm going to erase this, by the way. We're not going to need it anymore for now. When you think about that for a moment, I'm going to write down the full solution because I made a number of substitutions, going to substitute everything back to its original form. So while I do that, maybe you can take a second or so to think about how we're going to assign values to A and B. Because that's what you do, right? Mathematics tells you what the solution to the differential equation is, and physics tells you what to do with it. So that's that part now. In the meantime, let me write down the full solution. R theta phi t equals I var spherical harmonic theta phi e to the power minus e t h bar. There you go, in which phi r is, well, phi r by itself was 1 over r. Any ideas yet? In the meantime, just putting all the substitutions back in to get to our original form. And the u's, u bars in our case. Bessel's. Alpha. There you go. There it is. I think that's correct. Okay, any ideas? Here's a full solution. This is the solution of the Schrodinger equation, spherical harmonics, exponential with energy in it, and this thing is ultimately that thing over there. Okay, two boundary conditions, A and B.
Size of bar needs to be 0 at r equals 0.
Okay. No. It started out okay. Something needs to be 0 at some point. That's right. But not at R0. R0 is the position of your first nucleon. Remember the original problem. We have one nucleon. We're going to add another nucleon under the strong nuclear force. There's absolutely no reason for this second nucleon, the probability of the second nucleon, to go to 0 as you go closer to the first one. So in our original problem, where we had this similar problem in quantum mechanics with the infinite square well, that's when you said, well, at both sides of the well, it should go to 0. Because the potential was infinitely big at both sides. This is not the case now. There's no infinite potential of going very close to each other.
So it should be 0 when it's outside of the range?
Yes. Yes.
What was it 10 to the minus?
Yeah, well, we had a number for this. Well, let's call the number R0. So we do have this condition, that the solution at R0 should be 0. That is a condition. That's one. Again, having the two nucleons close to each other, there's absolutely nothing in our model that says that cannot happen. In a problem with infinite potential well of quantum mechanics, there we couldn't use that because of the infinite square well. Not here. Any more?
Greater than R0.
Sure.
Okay.
Greater or equal to R0, yes. Just the regular quantum mechanics, regardless of problem. Wave functions also always have to obey some property.
continuity.
Continuity, sure. No continuity here though.
Not at the
Not at the boundary. So it's not always saying that this is somewhat an unphysical problem, because you can get the number continuous, but not its derivative.
No, actually, it would still be continuous at the boundary. The derivative wouldn't be continuous.
Yeah, exactly. But yes, so
okay.
it's not differentiable at the boundary,
Yeah,
which
yeah.
is also physically impossible. So
Right.
it's another way of saying this is not a very good model. What do wave functions always have to obey, regardless of problem?
Its bracket should be 1.
Exactly. It's bracket, or in Schrodinger waveforms set, it should be normalized. This thing of all volume of all space should be 1. Any more? You know what it means physically, yes? It just means that if you go and look everywhere, you're bound to find a particle. The chance of finding a particle is going to be 100% if you make sure that you look everywhere in all volume. Well, one of them is kind of a trick question. There's another boundary condition. I can totally forgive yourself for not thinking about this yourself. Not only does this integral have to equal 1, it also has to not equal infinity. There was some grammar wrong in that sentence, but you know what I mean. Listen, if the integral, if you do the integral as it stands now, and the number is 8, happens to come out, you know how to get rid of the 8. You just define the a's and b's such a way that 8 is going to be divided out back to unity. Suppose that this thing is infinity for some reason. Now there's no way to choose a and b in such a way that infinity goes away. So that's sort of a third condition.
They have to be linearly independent.
No, those they are automatically.
Yeah.
These are already linearly independent. That's because it's a linear differential equation.
That the wave function can be written as a multiplication of 2 other functions.
Not a multiplication. Summation.
Summation.
There you go. It's sort of a third condition. You don't encounter this very often in quantum mechanics, because typically the examples that they choose are such that the thing never diverges anyway. It's always a number.
For the free particle it does, but then do the Fourier trick.
Yes. Yeah, you're right. Okay, now it so happens, and if you want to know the details, I can tell you, and if not, you can look it up. But it so happens that if you go and take this thing, right, these are the boundary conditions that we need. We're now going to assign values to things. If you take this, the one that we have now, and you do it over all volume, now this gets squared, this gets squared. Let's look at the R part of the volume. All right? So at the very least, in this integral, there will be an integral over the R part of the wave function, modulo squared. Do you know how to write this? It's dx, dy, dz, but you have to write it now in r's and thetas and phis. How to do it? The answer is? Sine squared theta, dr, d theta, d phi, yes? So ultimately, I'm just going to ignore all the parts with the phis and the thetas for now. I mean, they're important, but not for my condition here. So I have to integrate over the R values. What R values are there? From where to where do I have to integrate?
0 to 1.
Exactly. Because our potential ranges from 0 to the end of the potential. You can also integrate all the way to infinity, by the way. But then again, the Schrodinger function is going to be 0 outside of R naught anyway. So, okay, here's the thing. So this is what this is just the normalization. Neumann functions. They go to infinity at R equals 0. Now, again, forgive yourself for not knowing this, because who knows the Neumann functions by heart. But if you go and look them up, you'll find that these Neumanns here become infinite, plus or minus infinite. Regardless of the value of alpha, we'll always go to infinite. In other words, if you try to normalize this wave function that we have now, starting with R equals 0, you always get an infinite contribution. That breaks this condition here. So we have to get rid of the Neumann functions. And we should be able to do that, yes? Because we are free to choose our A's and B's. We don't want the Neumann part because it gives you infinite. We're going to choose B 0. This condition leads exactly to our choosing B 0. There you go. Now that leaves us one constant integration, A, but two conditions to fulfill. Now this one, we're sure now that whatever comes out of this integral is going to be a number. It's probably not going to be 1, but then we can solve by choosing A appropriately. No issue there. For my magic number part, I'm not going to need the actual number for A. But convince yourself that you can easily do this, yes? We've made sure that the outcome of this integral is going to be some number, not infinite. Some number comes out, choose A correspondingly, that this number becomes 1, and there you go. We have now exhausted all our boundary conditions, A and B. But still we have one condition. Our constant integration we have exhausted. We have now one condition left to fill, this one. Any idea physically what that will entail? One more boundary condition. This one will give you the number for A. Think back of the example with the normal infinite potential well.
Sine.
What's that?
Can you use sine here or not?
What do you mean then a sine?
Yeah, make A sine like something over not. So you can make it equal 0 or not, or is equal or not.
Not sure what you mean. No, there's something to do with me listening, not with you talking. So, you said something about a sign. Do you mean a sign is in the plus or minus, or a sign is in the function?
The function.
The function. A sign. Well, you know, it is similar though. If you go back to the original example that we did, we had signs. And we knew that the sign, this function, had to go to 0 at a specific point, namely the end of the potential well. And what we did was, well, we looked at the positions or the values at which signs would be 0. And we applied that, and then we found that energy could only come in certain lumps. It discretized the energy. Same here. We know something. We now have a solution that is now purely yeah, it's purely Bessel. There you go. It's that one. And we know one thing about this, this solution. It should go to 0 at the boundary of R0, because this is where the arm of the boxer stopped, where the strong nuclear force stopped pulling. So we have a condition. This one here, condition says that this Bessel function, that one, at this should be 0. In other words, this Bessel function, here it is right here, has this complicated argument that has the energy in it. At R0, this thing should be 0 itself. That gives you only certain values that the energy can have for this thing to be obeyed. And just as in the potential and normal quantum mechanics gave you an energy spectrum, the only allowed energy values, it also gives you the only allowed energy values. Let's write it down for a second. So in order to make sure that this boundary condition is fulfilled, or in other words that this is true, we're going to look up in a table. In fact, this is what we're going to do in the tutorial in a second. What the zeros are, the zeros of the Bessel function, in other words, the value of the argument such that the Bessel function itself is 0, we're going to call them J. These are the zeros, the values that make the Bessel function 0. And then we're going to say, okay, well that means that this whole thing has to be a j, one of these j values. In other words, a 2m e minus v divided by h, there you go, at position 0, r0, is equal to one of these zeros of the Bessel function. These we're going to look up in the table, because there's whole listings of values of where the Bessel functions are going to be 0.
Are those the same as the spherical Bessel functions?
No. No, the spherical Bessel function...
You're just using the same symbol.
I'm using the same symbol, yes. The spherical Bessel functions also happen to be called j,
yes.
But those are functions, these are numbers. It's my own little private notation. But you're right, spherical Bessel functions exist. It's really just this thing with an additional plus sign here, I think, or minus sign or something like that.
I think spherical Bessel functions can be decomposed into sines and cosines, but normal Bessel functions, these ones aren't tractable in any other form.
Oh, I see, okay.
I think that's it.
But you're right, the notation is the same,
Sorry,
but it's a number. Hey, but without going to go through the mathematics, you can tell that energies here will depend on the zeros of the Bessel function, and because these are discrete, energies will become discrete. In fact, without even doing the whole numbers, I can already tell you that E, the energy that is allowed to solve this problem, the energy that nucleons can have in order to solve a bound state, and to stick together, are going to be proportional to this number squared, with some other numbers thrown in. Okay, well, this is exactly where I wanted to come during the main lecture. Just as a final question. And we're going to work with this during the tutorial in a second. Remember that we wanted to get the magic numbers out. By the way, there's some number here, yes? And this number depends on the m and the h bar and the r naught and such. We can calculate that number. It's not important for my argument. I wanted to get the magic numbers out, these numbers. And I'm so close now, because I know the energies that nucleons can have when you try to squeeze them together to form a proton or a neutron. Excuse me, when you put the nucleons together to form a nucleus. We're so close. Now, when is a nucleus stable? Or more stable than the next one? Phrase in energies.
When it has lower energy?
Exactly. When it has low energy. What we're going to do in the tutorial in a second is we're going to use this formula that we now know is true. We're going to look up the zeros of the Bessel. For every next zero that you write down, you get another energy. So that means that energies will be discretized, and they will be some distance from each other. There will be an energy value over here, some low energy, corresponding to 1, 0. Going to take the next 0, gives you another energy level, a little bit higher. You take another 0, gives you another energy level, a little bit higher. Now something interesting happens. You take the next 0. All of a sudden, you just look this number up, you put it in, all of a sudden, the next energy level isn't here, all of a sudden it's over there. That means that you have a whole bunch of energy levels, energies that the nucleons can have, that are pretty low. Now, how many can you fit in each? It's an energy. It's a quantum state. You can put nucleons in. If you are a fermion, how many of the same fermion can you put into one quantum state? 2. If you're a spin 1/2 particle, and nucleons are proton or neutron, spin up, spin down. This one can have 2, that one can have 2, that one can have 2. All of a sudden, the next nucleus that you can make requires a lot more energy. So this group of energy levels grouped together is going to be a very stable nucleus. Because making the next nucleus will require all of a sudden a lot more energy. You take some more of these values, the next Bessel zeros. You get another group here. Then you take another one, the next 0, all of a sudden there's a jump again. with a number of energy levels. Every time that there is a jump, that means that it requires a lot more energy to make the next nucleus. And all the nuclei in between don't work that well. The only thing we're going to do in the tutorial in a second is count how many you can fit into these. It's going to be 2. We're then going to count how many you can fit into these. This next group is going to be 6. So in other words, in total it's going to be 8. It's going to be stable. And we're going to go all through the sequence and end up right about here. That's where our model stops. The big exercise for this week that we're going to discuss on Friday is going to replace our potential well, which now look like this, are not r as a function of v or so. I'm going to make it a little bit like this. Why would I do that physically? What does that mean? That it now has this arc instead of just this jump. I removed something from my model originally. I put protons together. And I said, well, strong nuclear force will take care of everything. Protons do something else too, except for feeling the strong nuclear force. Yeah, exactly. They repel. And if you add the repelling, then the Coulomb repelling, the electro repelling, will change this shape into that shape. One of the exercises, big exercise, is going to take you some work, because you have to go through this calculation with this little modification. You do that, find the next couple of ones. And then you have the magic numbers. And now you know which nuclei are going to be stable and which ones aren't. And okay, it's mathematics, but we only use quantum mechanics. Okay, going to make a start during the tutorial in a second. Yes?
So how do you get the rest of them then? The rest of the magic numbers, because this gets you a step further.
Yes. There's a part that we have thrown out from the outset, not just the Coulomb propulsion. They have spin, the neutrons and the protons, but they also sort of orbit around each other. This is very classically speaking. Consequently, they don't actually are little planet systems, but they have the same mathematical structure. And there's this thing in mechanics that's called spin-orbit coupling. It's orbital angular momentum, how much they are rotating around each other and how much they're rotating around their own axis, again, classically speaking, gives you a contribution to the energy. So there's another addition, except for the Coulomb propulsion, that has something to do with how much they're rotating around each other. That's another part that you can put in. And if you put that one in, you get, well, I forget, but you get somewhere further down the line. At this point, it becomes somewhat more tricky. People are not completely sure how to do this. Just as a historical factoid, I hate to say this to the women in the audience, but the person, yeah, there is a reason, trust me. Solving this whole problem in the way that we did now, or a similar way, including this spin-orbit coupling, was devised by this lady. Her PhD academic advisor won the Nobel Prize for this. That was somewhere in the 1950s or so. And in physics communities, this is still one of the most overseen scientists in the world, because this lady, as a PhD student, figured out how to do this. And then this guy, who not accidentally happened to be a man, won the Nobel Prize for the work that she did. I hope the times have changed. So, but yes, that is the answer. Sorry?
What's her name?
I forget, it's either Lise Meitner or it is Goeppert-Mayer. It's one of the two. We have to look it up. We can do it in a second.
I think it was Meitner because I recognize that name.
Okay. Well, we're going to look it up in a second. I mean, they both worked in nuclear physics, but I always forget which one is which. Which wouldn't happen if one of them had won the Nobel Prize. It would have been easier to remember. Okay, shall we reconvene at the other side?